Alright, so let's try something interesting here. Let's use Newton's method to evaluate a really simple first-degree polynomial to several iterations. Let's say, I haven't really decided where we're going to stop yet, but let's do at least 3 iterations to get up to an x4. Before we begin, if you aren't comfortable with Newton's method, or if you just want a refresher about the mathematical basis of the calculus of Newton's method, exactly how it works, how it looks on a graph when you perform these calculations, and why it works, what it's useful for, what it doesn't work for, when it fails, go ahead and check out my video, The Graphical Basis of Newton's Method, Graphical Basis, Mathematical Analysis Failure, something like that. It's on my channel under this playlist, and I think that would be pretty elucidating. So let's go ahead and get started. I want to evaluate this for, like I said, a crazy simple function. So let's do a first-degree polynomial. F of x equals x plus 4. Okay, how's that sound? And we're going to evaluate this with an initial x1 of just 2. Okay, and all right, what's our first step? Well, I think our first step to do Newton's method, we're going to need to know the formula for Newton's method. So let's go ahead and write down that formula. We should remember that it's xi plus 1 is equal to xi minus this rational here, f of xi over f prime of xi. Okay, so that's cool. Now, let's do our next step. What's the smartest thing for us to do? Well, I think the smartest thing right now for us to do is go ahead and take f prime of our original equation. Let's go ahead and take the prime of that because we're going to need it, and so why break up our math in a minute and break our continuity to stop and take the derivative? Let's go ahead and get that out of the way. So, x plus 4 prime. What's that going to be? Well, this is really not that hard at all. 4 is a constant, okay? And we all know that c prime is always 0. So any constant, no matter what it is, prime is always going to be 0. So we just ignore it because this is adding 0 to something which doesn't change it at all. So x prime, well, x prime, one of the derivative rules states that x prime is just 1. So the entire prime of all of this is just 1. That's all there is. So let's go ahead and write over here that... let's do this. F prime equals 1. So we have that in our arsenal of knowledge over here on the right. I'll try to give you, the viewers, you all, sufficient time to take screenshots if you into that kind of thing, if it's helpful for you, before I start erasing. From now on. So, all right, let's start plugging things into our function. Well, xi plus 1. Well, that's just saying what was the last x guess we had. You know, this is really written terribly. It needs to, the 1 needs to be more of a subscript. There we go. That's more appropriate. So, xi plus 1, this is just saying x1 plus 2. So, you just always, all this means is just add a number right there. Add a number to whatever this little thing was. So, x1 plus 1, xi plus 1, this is just x2, okay? For our first iteration is going to equal xi, which is going to be, once again, what the value of our x1 was, or 2. So let's just write parentheses here. It won't save you time, but it will prevent mistakes everywhere we're going to need to put that. Minus this rational, f of xi. Well, f is just referring to this original function, so parentheses plus 4. Now, this is really interesting on the bottom. The bottom is the prime of xi, but now what normally happens, if you've done Newton's method problems on your own, or you've watched some other videos, you'll notice that almost always the bottom still has a variable in it, which makes things considerably more difficult. But we have really got we've been really lucky with this function because the bottom now, f prime is just 1. There's nothing to plug in, so we're only evaluating 2 terms here. So let's go ahead and change colors and write in what our x1 is here. Our x1 is going to be 2 in both of these spots, right? From 2 there. So this is just some simple math from here on out. This is 2 minus, okay, 2 plus 4, that's 6. So 6 over 1. Now, what is 6 over 1? 6 over 1, this is just the same thing as 6. So this is just saying 2 minus 6, which we know is negative 4. So our x2, congratulations, we've arrived there, is negative 4. All right, so you can take a screenshot of that if you'd like. All right, I'm going to erase this now, and we're going to put our x2 up in our arsenal of knowledge here, which we're going to keep over on the right. We have our formula, and we have our x1. So let's rewrite our x1. We have x1 equal 2, and x2 equal negative 4. Okay. negative 4. Great. So x1 was 2, x2 was negative 4. We're going to have an x3 in a minute, and we're definitely going to have an x4. So we'll keep that there. We might even have an x5. Who knows? We probably will. So I'll probably feel like evaluating it out that far. So let's do some more work here. All right, let's evaluate for our x3. Let's do a second iteration. So we can think of this as iteration 0, 1, 2, 3, 4. So if it's confusing why I'm saying, all right, for our second iteration, we'll be getting x3, 2 and 3 aren't equal. I'm just saying this was what we were given, our x1. We were given that to begin with. So when we start here, this is 1, then this is 2, and we're always one number ahead on our x3. It's kind of like this is the year 2013, but it's the 21st century because we're already in the 21st century since we started the Roman calendar. So, all right, it's basically the same principle. Now, all right, let's do this. X3 is equal to xi, remember we're doing the parentheses thing, minus f of, what am I writing f for? Parentheses plus 4 because we're doing our f. And then over 1 because that was our prime, remember? And this is always going to be the exact same thing. For every single iteration, it's going to look just like this. That's not going to change at all. So we're just going to go in and plug in our numbers. In this case, we're plugging in negative 4 for both of these. So let's go ahead and do it. Negative 4, negative 4. All right, let's do the math. That's what this is all about, right? So we have negative 4 minus negative 4 plus 4. Well, that's just 0. And so 0 over 1. Now, this I might seem like I'm doing a bunch of obvious steps here that we can just do in our head, but if anybody is uncomfortable with this, I would like to make it as explicit as possible just for that individual's benefit. So, what is 0 over 1? Well, 0 over anything is saying basically divide 0 into a whole bunch of parts. So my calculus professor has said, and this is a really great analogy, if you have $0 and 50 friends, how much does each get? Nothing. So this is equivalent to nothing, right? So this is just saying negative 4 minus nothing. So negative 4. We're just going to be stuck at negative 4. It doesn't change. So our x3 is negative 4. All right, now you might be tempted to think, okay, I see a pattern. 2, negative 4, negative 4. Oh, we've arrived at our value. We're done. Negative 4 is the last step, the last stop on the bus. We're finished. But let's not jump to any rash conclusions here. I knew this was going to happen, so this is why I wanted to go ahead and evaluate out to x4 and x5 at least. We may even go farther than that if I'm in the mood once we get to the end of this. But once we get to the end of our fourth iteration. But, okay, why is it not a good idea to jump to that conclusion? Well, there are two reasons. One, because this math is unpredictable, and you can't just look at two things and think that you have recognized a good pattern. And secondly, Newton's method is an approximation. So if you think that you see a number, let's say we got negative 4, it's not going to happen, but let's say that we got negative 4 for the next 4,000 iterations. And should we assume that the point we're trying to approximate is exactly negative 4? Well, no, because Newton's method is exactly that, an approximation. And approximating a point means we're never going to be exactly there, we're just going to be close. So even if it's repetitive, as much as that might make one want to think that that's, oh, we've arrived at our value, that the point we're trying to approximate is, we can't go down that slippery slope. That is not an appropriate way to think about things. So, all right, enough of an aside there. Let's go ahead and start our third iteration to calculate x4. All right, cool. Let's do this. x4 equals xi minus over 1 parentheses plus 4. All right, so we have here negative 4. We have here negative 4 because that's our x3, right? And let's just do the math. So we have negative, this is equal to negative 4 minus negative 4 plus 4. What's that? Well, that's 0 over 1. We just determined last time that 0 over 1 is 0. So we have negative 4 minus 0 again. All right. We're in good hands. So we are at negative 4 again. The pattern continues. All right. So let's continue evaluating. Let's evaluate x5, do a fourth iteration. So x5 is equal to parentheses minus parentheses plus 4 over 1. All right, negative 4, negative 4. All right, does this look like the exact same thing? Yeah, I think it does. So, I did make a mistake earlier. I think I casually said, well, that's not going to happen, that we're not going to continue to get negative 4 again and again and again. Well, actually we are. We could do about a trillion iterations here, and if negative 4 always winds up right here, and we're adding 4 to it, well, what's that mean? That means that we're going to be just getting 0, and we're going to end up having negative 4 here as well, so it's going to be negative 4 minus 0 every time, so the value of negative 4 will never change. So we know that x5 is negative 4, and this truly is a pattern now. We can conclusively say after the first two, this was not enough to say it was going to be a pattern, but now that we've done this, we know it's going to be a pattern. So I can with 100% certainty say that my x6 and my x7 is going to be negative 4. And this is going to be negative 4. And my x anything, basically my x anything greater than 2, greater than or equal to 2, is going to be negative 4. So we approximate. Once again, it is still an approximation. It's not the exact point. So I think it was a good idea for us to do additional iterations on this problem. I do apologize for making that casual comment earlier that we're not going to get the same thing, because obviously we did. I just didn't work out this problem far enough ahead in advance. But all right, so let's do a quick recap here. We use Newton's method to approximate the function f of x equals x plus 4, which was a really, really simple first-degree polynomial. And we got some really, really simple, easy to calculate answers. The prime was really simple. The prime of that was just 1. Our x1 was 2, and so we evaluated that, and we got an x2 of negative 4, we got an x3 of negative 4, we got an x4 of negative 4, we got an x5 of negative 4, and we got basically an x anything greater than 2 is going to be equal to negative 4. So we're done. This is our final answer, and we are complete. So this obviously, if you watch my other Newton's method videos, looks a little bit different, or actually significantly, markedly different than the more complex evaluating using Newton's method for more complex polynomials. So I think it was good that we went ahead and did this. All right, thanks. Comment with any questions.